We're going to do section 3.3, graphical solutions today. 3.3.1, introduction to linear programming. Warm-up example. Graph the solution to the following system of inequalities. X plus 5y is less than or equal to 50. 2x plus y is less than or equal to 28. X is greater than or equal to 0. Y is greater than or equal to 0. Let's see here. I think I want to go to 20 on both the x and the y axis. So we go 10, 10, 5, 5, 15, 15. X greater than or equal to 0 is the vertical line. Y greater than or equal to 0 is the horizontal line. And we're limited to the first quadrant. So now if I go here, x plus 5y equals 50. The x-intercept is going to be 50, which is way off my graph. So I'm going to solve for y. Forgot the negative sign. So y equals negative 1/5 x plus 10. So go to the 10 on the y-axis, and then down 1 over 5. Down 1 over 5. And that should be a solid line. Okay, now for the 2x plus y is equal to 28. If I get an x-intercept, my x-intercept is 14, 0, because if I do the cover-up method, I divide by 2. But the y-intercept would be 28, which is not going to be on my graph, so I'm going to solve for y to get my slope. Subtract 2x from both sides. Get negative 2x plus 28, so we get a slope of negative 2. So down 2 to the right 1, or up 2 and to the left 1. And again, that will be solid. And I see 1, 2, 3, 4 regions. Now these two regions right here look unbounded because this goes on. But if you remember, this green line will eventually cross right here, and this blue line will eventually cross up here somewhere. So we got 1, 2, 3 bounded regions, 1 unbounded region. Let's pick a test point. I'll just pick 1, 1. A 1 plus 5, is that less than or equal to 50? Yes, it is. And 2 plus 1, is that less than or equal to 28? Yes, it is. So here is our shaded region. So now let's keep that in mind. Example 1. Now let's say we have a function f equals 2x plus y, where x and y are subject to the constraints in the warm-up example. What that means is I'm taking x and y from this shaded region, and because these lines are solid, from the edges of the shaded region as well. And we want to maximize f. Now I'm going to explain why this is true on the next page, but for right now, because I know my answers have to come from here, I don't want to just keep... One way you could do this, but we don't want to, is to take every single point in this region, plug it into f, and see which one gives you the largest answer. The nice thing about this is, according to the theory of this method, you just need to test the points on the outside of the shape. And even more particular, only the corner points. So since this is a quadrilateral, there are only 4 points I need to plug in. There's 0, 0, 0, 10. Now this point right here, normally it does not fall on such a nice point, but it is 10. 1, 2, 3, 4, 5, 6, 7, 8. It is 10, 8. So what we're going to see though in the examples is you have to set up this system of equations to solve where do these two lines intersect. So that's why we needed to do chapter 2 before this chapter. And then we have a 14,0 down there. Now if I plug those in, we get 2 times 0 plus 0, which is 0. 2 times 0 plus 10, which is 10. 2 times 10 plus 8, which is 28. And 2 times 14 plus 0, which is also 28. So to maximize f, I can either have x equal 10, y equal 8, or x equals 14 and y equals 0. And that is being represented by these 2 points right here. And what we're going to learn on the next page is technically, if I pick any point between those 2 points as well, those will also be a solution. And these all provide a maximum of 28. So the 10, 8, 14, 0 is called the location, and the value is 28. 3.3.2, solving linear programs graphically. A feasible region is bounded if you can draw a circle that contains the whole thing. Otherwise, it is unbounded. So, for example, if you have this region, I can draw a circle around the whole thing. So that one is bounded. But if instead we have this region, there's no way to draw a circle around the whole thing. So right there it kind of looks like it, but don't forget this keeps going on the outside. Even though I didn't draw it, it does. So that's unbounded. So this is an example of a bounded. And this is an example of unbounded. Fundamental theorem of linear programming for bounded regions. We are going to deal with unbounded regions, but if it's bounded, if a solution exists, it occurs at a corner point. How to solve a linear program graphically. Define the variables. Usually the question being asked gives a good hint to what these should be. Write the objective function in words, then in an equation. Write the constraint in words, then inequalities. Graph the feasible region, just like we did in 3.2. Identify the corner points, and like I said, sometimes this is going to be done by solving systems of linear equations, which is what we did in 2.1. Test all the corner points with the objective function and choose the winning point, the maximum or the min value. Write your answer in context of the problem. Now, I have this little graphic, and this is the best I could do. We have our x-axis down here. You have our x-axis right there. Got your y-axis right there. And this is what's called the z-axis. It's a third dimension. Well, when you have your objective function, it creates this sheet that hovers over the xy plane. And the reason why this is called linear programming is that this sheet has no bumps or curves in it. Because if you had something that looked like this, let me do my best. Imagine this is 3D. Yeah, that's coming out worse than I thought. Let me just do that. And then you have 3D. It's kind of shaped like a bowl. The maximums wouldn't occur at the corners. It would occur at the top of that bowl. So that's why you can't have any dips or curves in it. But it keeps going on forever. So what linear programming does is it graphs our feasible region, which kind of looks like a shadow underneath our objective function. Then it clips our objective function. So notice how I put bounds on it instead of it being unbounded. And then the reason why the corners must work is because if I draw a corner down there, and down there, oh, I forgot that corner as well. The only places that the maximum can occur is at one of these places. And it actually occurs at this corner in this specific one I graphed. So if you kind of think of this as a table, it should make sense why the maximum can only occur at a corner. Because if it didn't, the table would fall down to hit the corner, and then another one of the corners would go up, and so on and so forth. Now, the reason why we need it bounded is because if we had something unbounded like this one, this technically keeps going up forever and ever, so it will never attain a maximum. But as long as it's bounded, you will get enough legs to find the maximum. Like I said, I'm trying to draw 3D pictures on 2D isn't the best, but I hope these make somewhat sense. And that's enough for this video. We'll do more examples in the next video.